Suppose that two congruent polygons lie in parallel planes in such a way that their corresponding sides are parallel. If the corresponding vertices of these polygons, such as A and A' in figure 9.1a, are joined by line segments, then the solid that results is a prism. The congruent figures that lie in the parallel planes are the bases of the prism. The parallel planes need not be shown in the drawings of prisms. Suggested by an empty box, the prism is like a shell that encloses a portion of space by the parts of planes that form the prism. Thus, a prism does not contain interior points. In practice, it is sometimes convenient to call a prism, such as a brick, a solid. Of course, this interpretation of prism would contain its interior points. In figure 9.1a, segments AB, AC, BC, A'B', A'C', and B'C' are base edges, and segments A', B', and C' are lateral edges of the prism. Because the lateral edges of this prism are perpendicular to its base edges, the lateral faces, like quadrilateral A, C, C', A', are rectangles. Points A, B, C, A', B', and C' are the vertices of the prism. In figure 9.1b, the lateral edges of the prism are not perpendicular to its base edges. In this situation, the lateral edges are often described as oblique, slanted. For the oblique prism, the lateral faces are parallelograms. Considering the prisms in figure 9.1, we are led to the following definitions. Definition: a right prism is a prism in which the lateral edges are perpendicular to the base edges at their points of intersection. An oblique prism is a prism in which the parallel lateral edges are oblique to the base edges at their points of intersection. Part of the description used to classify a prism depends upon its base. For instance, the prism in figure 9.1a is a right triangular prism. In this case, the word right describes the prism, whereas the word triangular refers to the triangular base. Similarly, the prism in figure 9.1b is an oblique square prism if we assume that the bases are squares. Both prisms in figure 9.1 have an altitude, a perpendicular segment joining italics on height the planes that contain the bases, of length h, also known as the height of the prism. Name each type of prism in figure 9.2. Solution: A. The lateral edges are perpendicular to the base edges of the hexagonal base. The prism is a right hexagonal prism. B. The lateral edges are oblique to the base edges of the pentagonal base. The prism is an oblique pentagonal prism. C. The lateral edges are perpendicular to the base edges of the triangular base. Because the base is equilateral, the prism is a right equilateral triangular prism. Definition: the lateral area, capital L, of a prism is the sum of the areas of all lateral faces. In the right triangular prism of figure 9.3, A, B, and C are the lengths of the sides of either base. These dimensions are used along with the length of the altitude, denoted by h, to calculate the lateral area, the sum of the areas of rectangles AC, C', A', AB, B', A', and BC, C', B'. The lateral area, capital L, of the right triangular prism can be found as follows. Capital L equals AH plus BH plus CH. This equals H times the quantity A plus B plus C. This equals H times capital P, where P is the perimeter of a base of the prism. This formula, capital L equals H times capital P, is valid for finding the lateral area of any right prism. Although lateral faces of an oblique prism are parallelograms, the formula capital L equals H times capital P is also used to find its lateral area. Theorem 9.1.1. The lateral area, capital L, of any prism whose altitude has measure h and whose base has perimeter capital P is given by capital L equals H times capital P. Definition: for any prism, the total area, capital T, is the sum of the lateral area and the areas of the bases. Both bases and lateral faces are known as faces of a prism. Thus, the total area T of the prism is the sum of all the areas of all its faces. Recalling Heron's formula, we know that the base area B of the right triangular prism in figure 9.3 can be found by the formula B equals the square root of S times the quantity S minus A times the quantity S minus B times the quantity S minus C, in which S is the semi-perimeter of the triangular base. The general formula for the total area of a prism follows. Theorem 9.1.2. The total area T of any prism with lateral area L and base area B is given by T equals L plus 2 times B. Definition. A regular prism is a right prism whose bases are regular polygons. Henceforth, the prism in figure 9.2c will be called a regular triangular prism. Definition. A cube is a right square prism whose edges are congruent. The cube is very important in determining the volume of a solid. To introduce the notion of volume, we realize that a prism encloses a portion of space. Without a formal definition, we say that volume is a number that measures the amount of enclosed space. To begin, we need a unit for measuring volume. Just as the meter can be used to measure length, and the square yard can be used to measure area, a cubic unit is used to measure the amount of space enclosed within a bounded region of space. One such unit is described in the following paragraph. The volume enclosed by the cube shown in figure 9.9 is 1 cubic inch, or 1 inch cubed. The volume of a solid is the number of cubic units within the solid. Thus, we assume that the volume of any solid is a positive number in cubic units. Postulate 24, volume postulate. Corresponding to every solid is a unique positive number, V, known as the volume of that solid. The simplest figure for which we can determine volume is the right rectangular prism. Such a solid might be described as a parallelepiped or as a box. Because boxes are used as containers for storage and shipping, such as a boxcar, it is important to calculate volume as a measure of capacity. A right rectangular prism is shown in figure 9.10. Its dimensions are length L with W and height or altitude h. The volume of a right rectangular prism of length 4 inches, width 3 inches, and height 2 inches is easily shown to be 24 inches cubed. The volume is the product of the three dimensions of the given solid. We see not only that 4 times 3 times 2 equals 24, but also that the units of volume are inches times inches times inches, which equals inches cubed. Figures 9.11a and b illustrate that the 4 by 3 by 2 box must have the volume 24 cubic units. We see that there are 4 layers of blocks, each of which is a 1 by 2 by 3 configuration of 6 units cubed. Figure 9.11 provides the insight that leads us to our next postulate. Postulate 25. The volume of a right rectangular prism is given by V equals LWH, where L measures the length, W the width, and H the altitude of the prism. In order to apply the formula found in Postulate 25, the units used for dimensions L, W, and H must be alike. Find the volume of a box whose dimensions are 1 foot, 8 inches, and 10 inches. See Figure 9.12. Solution. Although it makes no difference which dimension is chosen for L or W or H, it is most important that the units of measure be the same. Thus, 1 foot is replaced by 12 inches in the formula for volume. V equals LWH equals 12 inches times 8 inches times 10 inches. Volume equals 960 inches cubed. The formula for the volume of the right rectangular prism V equals LWH could be replaced by the formula V equals BH, where B is the area of the base of the prism. That is, B equals LW. As is stated in the next postulate, the volume relationship is true for right prisms in general. Postulate 26. The volume of a right prism is given by capital V equals capital BH, where capital B is the area of a base and h is the length of the altitude of the prism. In real-world applications, the formula capital V equals capital BH is valid for calculating the volumes of oblique prisms as well as right prisms.